we're going to cover both what I call mature integrals and integrating absolute value. We're going to start with integrating absolute value because it's actually pretty simple. All right? If I want to integrate an absolute value problem, let's say that I wanted to integrate 2x minus 3, all right? And I wanted to integrate it from -1 to 5, but it's the absolute value of 2x minus 3. What would I do? You have to treat this as an area problem. All right? That's kind of the big thing, is you have to think area. All right? And especially if it's an absolute value of a linear. Isn't this a linear in here? Right? So you have to think, what does this graph look like? Well, let's start with an x-intercept. Let's set it equal to 0, and let's see. So if I set that equal to 0, I get 2x equals 3, and I get x equals 3/2. Right? So that is the x-intercept, which, now, is it possible that an absolute value function could be moved up? If you remember transformations, right? Yeah. But wouldn't it have to look like this? Wouldn't it have to be like 2x minus 3 plus 5 for it to be moved up like that? If that was the case, you could treat it as two separate integrals. All right, just so you know, if you run into that, you could treat it as two separate integrals. That's not the case here. I just have a regular old 2x minus 3 absolute value, which means its graph has an x-intercept, there's 1, there's 2, at 3/2, which is right here. And doesn't the graph of an absolute value, at least if it's a linear, right, isn't it a V? So doesn't it look like this? Right? So now what? Well, I'm integrating from -1 to 5. Okay? So if I'm integrating from -1 to 5, here's -1, 2, 3, 4, there's 5, all right? And my areas are this. Right? So we could do this problem with two areas of a triangle, couldn't we? That's one way. Think area. I want you to add up here method 1. Method 1 is to think area. Method 2 is to split this into two integrals. And no, I'm not talking about this over here. That was another example. I'm talking about split it into two integrals and do it analytically. How would I do that? Well, I need to go back to my function here. This is my 2x minus 3. If you remember how absolute values work, that's 2x minus 3. What is this side? It's the negative of 2x minus 3, which wouldn't that be negative 2x plus 3? So what you can do analytically, and the reason I'm showing you this is because sometimes you might need to be able to do it analytically without an area. You break this into two integrals. We're going to do this first integral in here as the integral from -1 to 3/2 of negative 2x plus 3. That's this part right in here. And I'm going to add that to the integral from 3/2 to 5 of regular old 2x minus 3. And that is how you integrate absolute value. Okay, and I don't want to spend a bunch more time on it because from there, you know, if I wanted to do this, isn't this a pretty easy antiderivative? And this is a pretty easy antiderivative. And then you just do the fundamental theorem of calculus and plug in your values. So you can either do area or you can do two integrals. But what did I have to know? Didn't I have to know the x-intercept? Right? And I had to multiply the negative part by a negative. All right? So enough on absolute value. Let's get to mature integrals. Now, believe it or not, these are called mature, but you really already know how to do a lot of what we're dealing with. Okay? We're just going to look at a bunch of examples here. And, you know, let's look at this one. And this is one that, you know, maybe one of the harder ones if you haven't seen it before. Okay, if I let u, okay, this is one, you know, we've been working substitution, so let's think. If I let u equal 3x minus 1, now on this one, let's go over to the side here and write my du, and you'll see why in a second. What's du? 3 dx. Well, I've got a problem. Why do I have a problem? Because this little x isn't there. Okay? So what I'm going to do is show you a new technique, all right, for integrating in this situation. All right? What I can do is solve this for x. My u equals 3x minus 1. All right? Let's do that. If I have u equals 3x minus 1, and I add 1, then I have u plus 1 equals 3x, and I divide both sides by 3, and I have that x equals u plus 1 divided by 3. Right? So guess what I've done now? I now have a way to represent everything that's up there. This is this. All right? Now wait a minute though. See this little du that we did? Don't I still need to introduce a 1/3? So what you wind up with is 1/3 times the integral of u plus 1 over 3 times the square root of u du. Now, don't I have a constant right here? Isn't that like a 1/3 times that? So I can pull the 1/3 out in front, and that 1/3 would be multiplied by this 1/3. So this would become 1/9 times the integral of u plus 1, the quantity, times, I would call it u to the 1/2 du. Now, would you like for me to finish that problem? Let's go ahead. So I have 1/9 times the integral of u plus 1, the quantity, times u to the 1/2 du. Now, I've already made my substitution. I can't substitute again. So what would I do? I would distribute. So I have 1/9 times the integral of u to the 3/2 plus u to the 1/2 du. Now I've got it split up, see, and it's just regular power rule from here. So I'm going to add 1 You know, 3 halves plus 2 halves is 5 halves. So this is going to become u to the 5 halves over 5 halves plus, same thing here, add 1 there, u to the 3 halves over 3 halves. This whole mess is going to get multiplied by 1/9. Okay? Yeah, we've got our old friend plus c out there. Sorry about that. Because it's an indefinite integral. So I multiply by the reciprocals, and I have 1/9 on the outside, and I have 2/5 times my u. Well, what was my u? 3x minus 1. To the 5 halves power, plus 2/3 multiplied by the reciprocal, times 3x minus 1 to the 3 halves power. That whole thing plus c. Now, that answer is pretty much complete. Couldn't I distribute the 1/9 through? I mean, I could. And that would give me what? 2/45 times 3x minus 1 to the 5 halves plus 2/27 times 3x minus 1 to the 3 halves plus c. Now the du goes away after we find our antiderivative. All right? That one is actually about as monstrous and ugly as they get. All right? Let's look at one that's not as painful. This would be example number 2. The integral of 4e to the x sine of 8e to the x dx. This one's actually much, much easier. What would I let u be? I would let u be 8e to the x. But I think this situation actually showed up earlier in the week, so it's good that we're going over it. If u equals 8e to the x, then doesn't du equal 8e to the x dx? So, here's my u, and here's my du. But I have a 4 here. There's a couple things you can do with this, whichever way your mind works better. Here's the way my mind works. My mind works better if I think of this whole integral as 4 times the integral of e to the x sine of 8e to the x. If I think of it that way, then what would I have to introduce here? A 1/8, right? I would have to introduce, if I'm thinking down here, I would have to introduce a 1/8. Okay? So that's the way my mind thinks. Your mind might think, well, there's already a 4 here, so I just need to multiply it by what? So, you know, I think better this way. Introduce a 1/8 times 4. All right? And now what do I have? The sine of u du. So what is 1/8 times 4? Isn't it 1/2? Put the 4 over 1, and I'm going to have 1/2 times the integral of the sine of u du, and from there it's pretty easy. Okay? From there, it's just 1/2 times the negative cosine of u. So that's going to be negative 1/2 times the cosine of 8e to the x plus c. Okay, so some of that is understanding what we need to introduce. I think your brains will work better if you just pull this constant out and just introduce what you're supposed to introduce, then, because it just gets kind of muddy the other way. All right? How about the integral of 5 to the x, natural log of 5 dx. Well, before we can even do this problem, we need to go to Rivendell. Let's recall something. If I want to do the derivative, let's say I wanted to do the derivative of 6 to the 5x squared minus 3. This is good review for us. If I wanted to do the derivative of that, that is your thing. If you wanted to look that up on your derivative table, if you had forgot, this would be like a to the u, a number to some power. And if you look on your derivative table, it tells me that the derivative of a to the u is a to the u times the natural log of a times du dx. Okay? So the derivative of this thing right here is going to be 6 to the 5x squared minus 3 times the natural log of 6 times the derivative of u. So what's the derivative of 5x squared minus 3? 10x times 10x. Okay? Now, something else. This is another recall. What's the derivative of x? Isn't it 1? And then, like if we're doing substitution, wouldn't we say 1 dx, right? So, what is the integral? If you see this, which you might someday, if I just see the regular old integral of dx, isn't it just x? Okay? So keep that in mind. So watch. On this problem, I need a new color. How about this pinkish? If I let u equal 5 to the x, then du, according to everything we just learned over here, then du is 5 to the x times the natural log of 5 times the derivative of x, which is just what? 1 dx. Well, what do you know about that? My du covers the whole thing. So when I put my new integral, it's just the integral of du.
So you can just not use.
I don't even need to use the u because the du covers it all. All right? New situation you hadn't seen before. The integral of du, isn't that just u? Of course, I got a plus c, right? So what you got to put your u back in. What did we say u was? 5 to the x. So your answer is 5 to the x plus c. Okay? A similar problem that I'm not going to work through would be this one. I'm just going to kind of let you see it. If I had the integral of y times 6 to the 4y squared minus 3 natural log of 6 dy. If I had that problem, what do you think I would let u equal?
Y, 6y.
I would let u equal 6 to the 4y squared minus 3. All right? Because your du is probably going to cover the whole thing again. What would du be? Maybe I'll just go through this a little bit more. Du would be 6 to the 4y squared minus 3 times the natural log of 6 times the derivative of this mess, which is what? 8y. Okay? So I have everything up there except for the 8, right? So I just need to introduce a 1/8, and it's the integral of du again, because du represents all of it. All right? I'm going to try to get through one more. The integral of 7 to the 4x minus 5 power. This is a similar type problem, but it's got one little quirky thing in it I want to go over. If I let u equal 7 to the 4x minus 5, then du equals 7 to the 4x minus 5 times the natural log of 7 times the derivative of this, which is 4 dx. Now, you might be thinking, well, that's kind of messed up because it doesn't represent everything. But wait a minute. These things right here are just constants. So guess what? We just need to introduce 1 over all this mess. 1 over 4 natural log of 7. And then the du does cover it all. So it's just 1 over 4 times the natural log of 7 times the integral of du, like our last two problems. And we will stop there for today.